Ben, Landon, Ebel. Appropriately, the song Good Times is on in the background right now. Because we are doing shear moment diagrams today. Good times, no doubt about it. Get this show on the road. Let's see. How do I want to teach this to you? Yeah, I think I need to introduce this a little bit. So let's do that. Okay. So this is very good because when I look at the syllabus, we get to start shear and moment diagrams a kind of a day early relative to the syllabus, which is really good because it's such a pivotal concept. That's something you really want to understand well. So and it might give us time for something else awesome at the end. But we're getting darn close. What are we, 2 weeks away? Is that right? Is it 2 weeks after today? I don't know. So we're going to tackle something that we've been ignoring, and I don't know if you've noticed it. So let's just think about it for a second. In the case of, say, a truss, if I had a truss like this that was going to span over a river, and so we'll come back and fill it in with a bunch of webbing and so forth. We have studied trusses, and so we talked about the fact that you can actually consider that as a solid, but ultimately we're taking this hollow truss, if you will, and coming back and we're looking at each of those individual members in it. We're trying to figure out kind of how much force is on each one. So we can find the force on each member. And of course, we use the method of, well, two methods, but we use the joint method where we looked at each joint to make sure each joint wasn't moving. But then we also use the method of sections, which I thought was really cool. I'll think about this carefully, where we said, hey, let's make a cut right there. And we'll just consider everything to the left and the right of it as though it was solid. So let me fill that in. So we'll treat that like it's solid and this like it's solid, meaning it's just strong, whatever. Good, who cares? It's strong. It's not going to fall apart. And then we can sort of skip all of those members and get it right out in the middle of that. That we called the method of sections. What we're going to do today is extremely cool in that we're going to do the same thing with a beam. So I said this before, but it bears repeating. If I put a beam over the top of some kind of a road bed or something like that, we've talked about how with or without forces on that beam, it's going to deflect or bend down. And we've also talked about how the lower members of this are lengthening and thus their intention. I'm very interested that you can kind of visualize that because that'll be very important for those of you going on. And the upper members, though, are actually going to be getting crushed together, shortening, and so they're going to be under compression. And so what we've been ignoring is what's happening inside of that beam to keep that from happening. Does it make sense that a beam could be weak enough that the top members actually could crush? Maybe you're familiar with balsa wood, but it's not very strong. And so, if you try to crush the top members of balsa wood together, they're probably going to crush together. It's not very resistant to compression forces. And so, I can take a beam and push on both sides, or a post in the case of construction, and put a bunch of weight on it, and it can actually crush, if you will. But then the bottom members are going to rip apart under tension. And so, what's happening inside that beam? We have to figure that out. In other words, it made sense with a truss to look inside it because we actually saw the individual members that made up all the triangles. But isn't there also stuff inside a wooden beam? And just because it's solid doesn't mean it can't fail. And so that's kind of what we got to look at today based on the method of sections. And so let's see, I'm trying to decide if I want to just jump right into an example. I'm kind of thinking yes. So let's do this. So this is what engineers typically do to show supports. They'll just put a little point there. So this beam is simply supported, just like it was a second ago, sitting on top of those two concrete walls. And let's say let's make this beam, let's see, I don't want to repeat myself because I've got an example we're going to do in a minute. What size was that example? So let's say, I don't know, this thing is 14 feet long. And let's put a distributed load on it. Notice it's not triangular, but let's put the simplest load. And this is what happens on a kind of a typical house. We've talked about that a little bit, but let's put a load up there and say, I don't know, it's 580 pounds per foot. Well, as you know, if I take 580 pounds per foot and I multiply by 14 feet, then 580 times 14 tells me how much weight I have. That's 8,120 pounds. And notice, because this is symmetrical, does it make sense that the reaction at both joints, I guess I'll call them A and B, they'd be equal in this case, wouldn't they? Because everything is symmetrical. So I could just cut 8120 in half, and then I would be able to say that I have 4,060 pounds of reaction at A pushing up, and 4,060 pounds. We did this with trusses. We did this with everything. So awesome. This is now in equilibrium. There's 8120 pushing down. I just made 8120 pushing up. The beam is not rotating because of moment. And we didn't need to use moment to calculate this, but if we did, it would work. Maybe we'll check that really quick. Let's check the moment. So are the sum of the moments around, say, point A equal to 0? Well, let's just check and make sure that's the case. So what do I have? Well, because of the topic we just dealt with recently, would you agree that the center of mass of this beam, we don't have to do much calculation for this, the center of mass, or the center of the beam, would actually be in the center. And so there is 8,120 pounds pushing down in the center of that beam. So we reduced the billion forces to just one force, and it would be in the middle. And so what do we have for the sum of the moments? Well, we have 4,060 pushing positively a distance of 14 feet from A. And then negatively, we have 8,120 pounds pushing at a distance of 7 feet. And we're sort of hoping that that's equal to 0. And indeed it is. Check. So it's not rotating either. But we didn't have to do that this time to figure out 4,060, because we knew it was symmetrical. So we knew it'd have to be split evenly. If that was a triangular load or a trapezoidal load or some different type of loading, or if I came back and I took part of it away, let's take part of it away and say, oh, that only exists up to here, and there's like a whole bunch where there's none. That would complicate it. Or if I came back and said, no, let's now add one more force to this. Let's just randomly throw, 1,000 pounds right there. That's going to screw up the 40/60s. Do you agree with that? And because of moment, we'd be able to calculate how much was at each location. So I'm hoping you feel good about that. And so this is a fairly simple example. Okay, so what's happening inside the beam? And so we're going to actually use the method of sections to take a chunk of this beam and kind of look inside it in exactly the same way that we did up here. We're just going to chop the beam open and see what's happening inside of it, so that we can choose the right beam to make sure it doesn't tear apart or crush. So let's do that. So if I come over here and I put 40/60 and I draw my beam, except for I get out here some certain distance and I say chop. And what distance will that be? Well, let's call it a distance of X, because it's actually got to be everywhere. In other words, you actually have to look at every part of the beam and make sure it isn't going to break anywhere. Does it make sense there would be different forces in different locations on that beam? So we got to kind of look at all of those. That's the interesting part of this. Now let's think about what we have here. If I come back and add in my forces on the top, which I want to do now, let's make those in orange, let's say. And we said that was 580 pounds per foot up there, 580 per foot. Do you see, this is very important, do you see that the sum of the forces in Y now is not equal to 0? So the interesting thing about equilibrium is I need the entire beam not to move, but I also need all the pieces not to move. I mean, isn't this kind of the concept of the method of sections and the method of joints? Like, didn't we just look at one joint at a time and we said, okay, let's forget about the complexity of the bridge. Let's just look at that joint right there and make sure it doesn't move up or down. We looked at every single part, and every single part of this could not move up or down or right or left or rotate, right? That's what equilibrium meant. And so isn't that still true in a beam? Just because a beam is solid doesn't mean we don't have to think about that, because remember, just because a beam's solid doesn't mean it's strong enough to do the job. And so if I look just at this section, doesn't it also not have to move? I mean, didn't we do this with the method of sections? We took some slice out of a truss and then we said, okay, now the sum of the forces vertically, doesn't that still have to be 0? So how's that supposed to work? Well, let's figure out the sum of the forces in Y. I certainly have 40, 60 pushing up. What do I have pushing down? Do you agree that I don't have as much as I used to have? How do I figure out what that is? Temporarily, let's actually go back here and put a number in here. I'm going to say, I don't know, 5. If I decided to go 5 feet in, then wouldn't I have 580 pounds per foot times 5? That's not equal to 0. That's not good. The overall beam needs to not move up and down, but even the pieces of it need to not move up and down, just like they do, just like they were on the truss. How are we going to fix that? Well, remember, this actually is attached to something, right? Isn't that what we did with the trusses? When we did the trusses over here, and we were looking at, say, the left side of this, we said, well, it's not like it isn't attached. In other words, we actually drew that arrow, and we drew this arrow, and we drew this arrow. We drew those, and then we ignored the right side of it. But those exist as structural forces because they actually are attached to something. And so isn't our beam attached to something too? So here's my beam. Let's pretend it's connected in the middle. Why can't this side of the beam move down? Well, because it's connected to this side of the beam. Like, this can't move down without this one moving down too, right? So if this side wants to move down of the beam, isn't this side lifting it up? Like, it's connected to something. So there's actually a vertical force there by connection, right? This side can't just slide down with this side not moving because of the internal structure of the beam. And so we can actually come back here just like we did for the supports and say, this is not all the arrows that are in this picture. If you chunk it up like this, there's actually what's called a shear force over here. And I'll draw it. We'll talk about this in a minute, but I'll draw it downwards. Now learn that word, shear. What is shear? Shear is a beam or some member doing what I just showed you, which is sliding past each other. So you've seen this kind of a fault in an earthquake where one side of the earth kind of slides down relative to the other. The dirt wasn't strong enough to hold that apart. Well, a beam can do that too. Shearing it off means kind of like scissors. You sliced it. And so there's a force missing here, just like for the joints. When we showed that a beam was connected at the corner by a fixed joint, we said, hey, that fixed joint is going to provide some resistance, right? We said that's not going to let it lift up or push left or push right. Well, isn't that beam attached to something? So wouldn't there be some shear force there? Well, that's how we make this equal to 0. And this is so important. So watch this. If I go back here then, and I say minus V, notice V is down, then I actually can get this equal to 0, can't I? So if I do the math on this, I end up with, yeah, V, if I add it to the other side, would be 4,060 minus 5 times 580, which is 1160. Do you understand what that means? That means that at 5 feet in, that beam better be capable of resisting, and think of it as like, one hand up here pushing down and one pushing up. If it's trying to go like this, does it make sense if you pushed with 1,160 pounds of force, that beam better not go and slice in half, otherwise it's going to actually fall. Do you see what I'm saying? In other words, the internal structure of that beam has to be working. It's doing something. Just like the internal structure of a truss was, except in a truss, there's only a few members. And so we could actually look at them and calculate them all. Well, it's exactly the same thing we're doing here. We're just calculating what must be going on inside this beam. 5 feet in, there's 1,160 pounds of desire for that beam to just tear in half, if you will. So are you seeing this? So let's say this book is the beam and it's sitting right here. Does it make sense if I push down on this side hard enough, at some point the book would tear in half? It would push hard enough to tear in half. But the book is pretty strong. I mean, I'm not going to be strong enough to push hard enough to tear that in half. But that's kind of what's happening internal inside the beam right there. In other words, we just discovered that beam better be able to hang on a little bit. Well, let's take a look at something. Let's see here. I was not prepared to show you this, but this is definitely something I should show you. Where did engineering go? Somehow it got down there. So I've showed you this chart before that Boise Cascade gives for their beams. And notice this category right here. We've talked about allowable moment a little bit before, but what about allowable shear? We just got 1160 for the shear. Do you see this beam right here? This beam is 1.5 inches wide. That's pretty small. And it's only 3.5 inches tall. That's like a 2x4. It's a pretty small board. And it's saying that it can handle about 1,000 pounds of shear. In other words, if you put 1,000 pounds on this, it's going to slide in half. So if the beam that we just designed a second ago when I was writing on it, 5 feet in, required 1,160 pounds of shear capability in that beam, well, if we don't want to choose a 3.5 by 1.5, do you see what I'm saying? Because it can only resist internally this much force. You see the power in that? Do you see why this is so important? It's not just will the beam break in half because of moment, it's will it slide in half. if you put weight on it. Now, did you notice I just randomly picked 5 feet? What's 5 feet? Well, the answer is nothing special.
So if if you're gonna go more, have more distance from the left side, which is 460, our shear value is gonna go up.
Yeah, let's go figure this out. So what if it wasn't 5? What if it was at x equals 4, let's say? No, you said more. Let's go x equals 6. So this was at x equals 5. Let's go x equals 6 feet. Well, isn't it the same calculation? You still have 4060, but now you have 580 times 6 going down. What do you get now? You get 580. A totally different answer. And notice, surprisingly, it's the opposite of what you thought, Evold, which is the natural response, I think. It's actually smaller. Isn't that weird? Seems like it would have been more. Well, why is it not more? Take a little closer look at this. Why is it actually not surprising it was less? Well, the further we go this way, don't we get more weight above, which is helping resist the 4060 that's pushing up? And therefore, we actually need less shear. We need less internal force to actually fix this. What happens if we go the other way? Let's go down to say x equals, I don't know, 3 feet. That'd be 4060 minus 580 times 3 minus the required shear value inside the beam. What do I get when I do that? Oops. I actually get V is 2,320 pounds. Whoa, all of a sudden that beam, we got to choose a much larger beam. We can't design the beam off of 1160. We got to find the place where the shear is the worst. Does that make sense? Where's the biggest shear possible? Well, notice it seems that the closer we're getting, the shorter we're getting. Like if x equals 1 foot, I wonder what happens. 4060 minus 580 times 1 minus v equals 0. Whoa, we're going to get a really huge number for this. 3,400. 3,480 pounds of shear when that distance is 1 foot in. Whoa, we're going to have to choose a way larger beam. Are you tracking with me here? So what we're actually after is the maximum shear. There's like different shear. There's different shear values at every point in the beam. Let's do one other weird thing that you'll be surprised by. What happens if we choose X to be 7 feet? You punch that into your calculator. What is V? Notice 7 feet is in the middle of the beam. What do you get for the value of shear required for the beam in the middle?
0.
None whatsoever. In other words, in the very center of the beam, there is literally no desire. There's no force there because the upward force of 460 and the downward force that also happens to be 460, 4060, they're identical. So there is no desire for the beam to rip in half. And so if you think about it, that actually makes sense, because if you think about these arrows right here, if you think about these arrows pushing up right here, isn't that where all the force is? In other words, if that's where the fingers are pushing up on the beam, then that's where the beam is being pushed on the hardest. If you chose X to be 0 feet, then V is maximum, and you actually get 40/60. That's the worst place. In other words, if you're going to design a beam, does it make sense? You got to figure out the biggest number you can possibly get. Like all those red calculations I just made, you don't need any of those. You need this one. Now let's go back to that sheet. So the shear maximum, the maximum shear required by our little design we just made, and that's a super common beam design. It's what I design in houses every single time. It's that exact design. So now can you choose a beam that's big enough? Notice allowable shear. Well, where's a beam in there that is not going to shear off right at the end where the post is supporting it? Notice none of the beams that are 1.5 have a big enough answer for that question. This is the first one.
Right now.
What's that?
So we can't see the screen right now.
You can't? I thought I shared.
Oh, yeah.
Maybe I failed to share. Thank you. So we need a beam that has an allowable shear that can handle shear of 4,060 pounds. Notice there are none that are 1.5 inches wide. However, this one, there's the first one right there. Do you see what size that beam is? It's 1 3/4 wide by 14 inches tall. There's enough wood there that that beam will work. Notice if you get a much wider beam, like 3.5 inches, then it doesn't have to be near as tall, like this one right here. Notice the factor of safety there, like we only needed 40/60, and that's 4,800, so there's safe, but it's like a 3.5 by 7.25 inch beam would support this load in terms of shear. Like this is your job as an engineer. You got to look at that load, and I showed you how those distributed loads actually get applied based on the weight of floors and the projects we did. I showed you where those come from. You've got to be the one that chooses the beam. And so shear is one of the components you got to figure out. It's the internal structure of the beam. Is the beam strong enough to resist the fact that it wants to slide past? Notice some of these bigger ones are just massive. Look at that guy. 3.5 inches wide by 20 inches tall. It's almost 2 feet tall, and it can handle 13,000 pounds of shear. That's awesome. Again, I'm very interested in doing what I can to give you a conceptual understanding of this so that you kind of see it. I guess my question right now is do you see that this is the method of sections that we did for a truss? It's just that trusses have a minimal countable number of members inside, and we had to calculate all of them. Well, the inside of a beam has got to be calculated too, but it's just there's, well, infinitely many of them. And so we got to look at worst case scenario. So now let's make this really cool. What if we don't choose 5? But we take it back to what I had earlier, which is X. Let's make an equation for this now. So to get the shear diagram, diagram, well, I'll show you what I mean in just a second. All we're doing, because shear is just vertical force, we're saying what is the sum of the forces in Y? We know we need that to be equal to 0. And so we have 40, 60 going up. We have 50, 580 going down, but times the distance of X. Like we don't have to say 1, 2, 3, 4, 5, 6. We can say X. And we have shear going down, and we need this to be equal to 0. Would you agree then that V is equal to 40, 60 minus 580X? That's actually a graphable equation. And we can use that equation to find the maximum, because remember, all we really want is the maximum. Let's graph this in Desmos, because Desmos is cool. Let's see, will it let me say V equals instead of Y equals? Let's find out. I don't know the answer to that question. 40, 60 minus 580X. Yeah, I didn't mind. Now, notice you get predictably a really steep line. Like, isn't that a line that crosses at 4,060 and it has a slope of negative 580? So no wonder it's so vertical. So let's go to the little wrench up there and adjust the window a little bit. My beam is from 0 to 14. That will help because that's all the longer the beam actually is. And then the y-intercept up there is at 40, 60. So I need the y max to go much higher. So I'll say 5,000. And I'll just make the z, the negative value, negative 5,000 as well. There, that's a much better drawing. And technically, I really don't want anything except for the beam itself. In other words, I want X to stay between 0 and 14. So it would actually be better if I went in and chopped it off. That, my friends, is a shear diagram right there. Notice at 7, it's 0. Isn't that what we calculated a little while ago? And let's do something kind of cool because we can do this inside of Desmos. If I call that not just V, but V of X, then I can come down here and say, let's just figure a few things out. Like if I put in, we did this a while ago, if I put in 5, then what's my shear value? Well, let's just ask the Desmos to tell us. Isn't that the answer we got? At X is 5, wasn't the shear 1160? So this diagram is actually telling you the shear every single place in the beam now. That's what's so cool about it. Do you understand that? So we didn't notice it at the time, perhaps, but the relationship here is actually linear. In other words, if you double X, you're going to double the shear. Let's do something even cooler and go back and make this slidable. So I spent a lot of time with you, those of you that I taught calculus and this concept, but remember we never figured out 2. When X is 2, it's 2,900. And so I can slide to any place that I want to slide to. And notice that can include decimals. Notice I'm at 4.5. Do you see I have a formula now that tells me the shear any place? That's much more powerful than just finding the shear at one place. And of course, does it make sense to you that just from looking at the graph, I can kind of tell that that spot right there is the maximum shear. So that's what I need this diagram for, is to get the 40/60, the maximum shear. And this will get more complicated the weirder we load this beam. Right now we have the simplest load on it we could possibly make. And then notice out there at 14, what do you notice the shear is there? Notice it's the exact same answer, but it's negative. Now, that's kind of weird that that's negative, but we'll talk about that in a little bit. So that's a shear diagram. It tells you the shear everywhere. We're making a formula for this out of X instead of actually calculating it at a particular point. We now know everything. That's extremely cool. Now, just so that you have a sense of the negative, let's go back and kind of, well, redo this. Well, maybe I'll erase this just so that it's clear, but does it make sense that if I went back here and replaced this 7 with like a 12, does it make sense you're actually going to get a negative value for that? All it means is that instead of the beam kind of sliding this way, now when you get on the other side, it's actually sliding that way. Does that make sense? It's just a question of direction. So, you know, which way is it going? Is it getting pushed this way or is it getting pushed that way? That's the idea. So there's the shear diagram. Awesome. It's a graph.
This whole graph is from the perspective of the left side, right? So
yeah, nice job. Notice I just kind of randomly picked the left. And so we got to, what about the right side? Well, we got to talk about that too. We're going to get the same set of answers looking at it from the right side. And so we'll get to that. That's a good observation you make there. Now, what's the other thing? There's two things we always had to make sure never happen for equilibrium. One of them was, let's not have this graph translating up and down or right and left. Notice there's no forces on this that are right and left, so we don't really need to worry about the sum of the forces in X. It isn't really going anywhere. Nothing's pushing on it that way since all of our weight is vertical. But don't we have to worry about it rotating? So what about moment? So this is our huge takeaway. This is what we want to be able to do, is draw that shear diagram. And maybe I'll throw this in here really quick. And this, so that shear equation and this shear diagram, we need to have both of those. So this is actually the shear diagram. That's why it's called a diagram. The cool thing about a graph, as you know, is you're actually seeing the answers. You don't have to just have an equation. And that purple equation is really cool. But remember, if you're going to look for the maximum, isn't the maximum clearly right there? And so the diagram version of it allows you just to look at it and see what that is. And so now that I know that, I know what beam to choose. Does it also make sense because there's not much shear in the middle? Does it make sense if there was such a thing as a beam that was actually built like this? Does it make sense that beam would structurally hold up? It's just that costs more money to try to cut a beam like that than it does just to cut the entire beam. But it basically is telling us the middle of this beam doesn't really matter that much. a matter of fact, we could even really skinny it down to almost nothing, like make a bow tie out of it, and it would actually do the job, because more and more shear strength is required as you get to the ends. And so really thick on the end and really thin in the middle would actually work, wouldn't it? Now for steel, some steel could be made by pouring steel into a form. And if that's the case, that'd be a good thing to do. But that's kind of the power of this diagram. We're looking for the shear max, and then we're just going to choose a beam that can handle the maximum. And so there's a waist in the middle. Fine. It's cheaper to build that way. What about moment, though? Again, let's go back and consider our original graph here. Let's take this guy. Can't remember if I already copied this, and I don't need to copy it again. What about moment? Again, that start with 5 feet. And we had earlier called this point A. And so don't I need the sum of the moments around A to be 0? Remember, the method of sections, we don't know about the other side of the beam. We just know it's connected there. And so I'm going to switch this to an even number just to make our life a little simpler. Let's say that distance X was 6 feet. Then would you agree that 580 times 6, in order to figure out the moment, what I want to do is take those million forces that are up top up there and reduce them just down to 1. And so if I take 580 times 6, I get 3480. And it'd be pushing right in the middle of that 6 feet, wouldn't it? So I just reduced all those forces to 1. Again, you should think, yeah, I get that. That's what we've been talking about. So notice 4060 is pushing right at A, so it's not causing any moment at all. And so with respect to the sum of the moments around A, this is not good, because I'm not going to get 0. I'm going to get 3480 pushing clockwise, which is actually negative, and it's a distance of 3. That's it. That's all the forces there are. That's not good. That is not equal to 0. So do you understand that, again, because the beam is connected, that there would be a moment? In other words, if this beam is actually connected, if just like the shear, watch this carefully, if this beam wants to rotate down, and let's pretend we're just looking at the left side, is that side going to be allowed to rotate down? The answer is no, because it's being lifted up by this other side over here, isn't it? So do you see why I would need to add this moment to the support? Now, didn't we already do this? Let's think about this for a second. Like if I told you this beam was welded to the wall right here, didn't we say because that was a fixed connection that provides vertical support, it provides horizontal support and moment support? In other words, we added those earlier. Well, isn't this fixed? I mean, isn't that connected to something? It's no different. It's connected to something. So of course it's got shear moment. It's got vertical resistance. And by the way, it even has horizontal resistance because the beam's not going to pull apart. We just don't have to calc that right now. So this is a fixed support. I'm going to go ahead and draw that in. A lot of times this direction is called normal because it's perpendicular. I mean, it's no different than a fixed support because it's fixed. So it's going to have all of those. It's going to have a force in Y component, a force in X, and it's going to have a moment. It's going to have all those. So, well, thank God that's there, because that moment is going to be what keeps this beam from breaking, if it makes sense to you. Wait, That's not the only one. Isn't there another force here that we forgot? Isn't this V? Isn't that also doing some moment? Isn't that, wait a second, that's, oh, that's going in the same direction. It's negative, and isn't it at a distance of 6? But earlier, what did we learn? At 6, wasn't that 580 pounds that was V? So I know what V is at 6. As a matter of fact, I could just go use that formula we just made a second ago if I didn't. Couldn't I just plug 6 into that? 460, 4060 minus 580 times 6, it's 580. So I actually know the answer to that. And would you agree that that M is a positive because it's going, at least the way I drew it, it's going counterclockwise. And so doesn't this have to be equal to 0? So I solved this for M by adding all the other junk to the other side. It's all negative. So if I add 3480 times 3, 3480 times 3, and I add 560 times 6, I'm sorry, 580 times 6, I get 13,920 foot-pounds of moment. And again, notice that's at x equals 6 feet. Whoa, 6 feet in. That's a big ask. Do you agree with that? Now, remember my idea a minute ago? Hey, cool, man, let's build a beam that has no middle. Does it make sense? The moment says, better not do that. There's no shear there, but that middle's got to be able to resist 13,000 pounds, 14,000 pounds of desire to rotate. So guess we better not have nothing in the middle. That works great for shear, but it doesn't work very good for moment. Whew, that was a bad idea. Let's go back and look at our chart for a second. That was almost 14,000 pounds of moment. What beam did we pick a minute ago? We said this beam right here, right? That'll do shear, right? A 1 3/4 by 14 will handle the shear. Notice it also has an allowable moment. Will that handle the allowable moment? Not quite. See what I'm saying? Like, we got to make sure both things work. This is just equilibrium. We got to make sure things don't move up and down and they don't rotate. Well, that beam's not strong enough to keep that from rotating. It was almost 14,000 pounds. So we'd have to jump down to this one. Does that make sense? It's overkill in shear, but it's big enough that it would actually handle the moment. So a beam has a certain amount of allowable moment interior to it. In other words, just structurally how it's held together, the glues and the type of wood that you use. This is pretty cool. So I got to consider both of those. Unfortunately, you're not going to get to moment of inertia here until you talk about strength of materials next term. But I want to teach that to you because it's so awesome. But I guess I won't go down that rabbit hole right now. Now, the other problem is, and please understand this, think really carefully with me. Why did what we just choose for moment? Why did what we just choose for the moment? Why is that not a good idea just yet? Why are we getting ahead of ourselves looking for a beam that can hold 14,000 pounds a moment?
So we have to look everywhere on that beam to see what the maximum moment is.
Exactly. Don't we have to find the maximum? We can't just look at the first plot we want to look at, 6 feet. What if there's some place where it's worse? So again, let's play around with this a little bit. Let's do another couple of examples. Let's see. I don't know. Let's do it at least one more example. Let's do it at x equals 2 feet, like way closer to the side. And so at 2 feet, we'd have, well, let's see. Notice it's not negative. Notice it's not 3480 anymore, because that 3480 right there was 580 times 6. But we're only going to have 580 times 2 now. So that's going to be a much different number. So that'll be negative 1160. And if this was 2 feet, then the halfway point would be 1 foot. So it's a much smaller number at a much smaller distance. Minus v times 2 plus m equals 0. But what's the shear at a distance of 2? Well, we calculated that earlier. I think we calculated that earlier. No, we didn't. So let's just use this formula. If I put 2 in here, won't that tell me the shear? So 4060 minus 580 times 2, 2900. So this is 2900 at x equals 2. Okay. So I have m equals, this time, if I add that 1160 to the other side and I add 2900 times 2 to the other side, I get 6960 foot-pounds. Hey, it's a lot less. That's interesting. If we got really close to the support on the side, the shear got really big, but the moment actually gets really small. Isn't that kind of interesting? This is why we need a moment diagram, not just a shear diagram, but a moment diagram, because we need to see where the biggest moment is. And I can't sit here all day just guessing and checking, right? If I can graph them all, let's see if we can actually find not the moment diagram, or not a couple of examples, but kind of do what we did back here in purple. Can we write the moment diagram? Can we actually write that equation as an equation? Let's try it. So I'm going to copy this and erase some of the stuff on it. For the sake of the notes, let's go back and erase a couple of things on there. But so down here, though, what I'd like to do now is say, let's not have that one practical example. And let's not have that. Let's have that be x now. So the question is, can we write a formula? Can we write a formula for the sum of the moments, except for at x, not at 6, not at 2. So the question is, can we just do the same thing we did just a second ago? So the sum of the moments around A, what did we do a second ago? Well, we said 580, didn't we go up here? Didn't we say 580 times 6? That's how much weight this was. So this will be 580 times x. That's how much weight it will be. That's its weight. So that's kind of the force. What's the distance? Where's that located? How far is it away from A? If I was to put that in this picture right here, it'd be in the middle, right? So how far is it away from A?
X divided by 2.
Yeah, half of x, x divided by 2. That's its distance. So that's what we did a second ago, right? When this distance was 6, we said, oh, it's in the middle. So then that means the distance of the force that we had was times 3. And then the V, the shear, is whatever its size it is times an entire distance of x. So let's include that. And notice that was negative because it's pushing downward, right? So I got to throw that negative in there. And then so is the shear. So we have minus V times the shear times the distance of x and then plus m. And we need all of that to be equal to 0. And what is V? Well, we figured that out. It was this equation, 4060 minus 580x. So let's see, let's try to solve that equation for m. So let's see, I'm going to add this over to the other side. So I've got m equals, that would be 580 times x, since there's 2 of them, right? So x squared divided by 2. And then this would be plus v times x, which would be 4060 minus 580 x times x. Is that right? You agree with that? So let's see, what is that? That's 250, 290 x squared, and then 40, and then minus 580 x squared because of this one, and then plus 4060 x. So final answer, m equals, I guess that would be 4060x minus 290x squared. There's our moment equation. Hey, a parabola. That's interesting. Let me stare at this for a second because I'm okay, life is good. So let's go over to Desmos and see what that looks like. Now it's actually kind of hard to graph these on the same window because shears were pounds and we found ourselves between 4,060 pounds and negative 4,060 pounds. So I'm going to do these entirely separately. I'm going to just kind of get rid of this one and say the moment as a function of x. And we got 4060x minus 290 and then that X was squared. Do you see what I mean about the units? Look how much higher this went. Does it make sense we are after that point right there? Isn't that the highest M? What is it? Oh, good thing we figured this out, because the highest one was more than 13,900 or whatever. Let's check to see. Let me fix my little slider deal so that it can do all of our work for us. Let's see if it's working. A minute ago, we tried 6. Isn't that what we got? 13,920. So that's the moment there. We also tried 2. Isn't that the answer we got? I don't see it. Where is it? Oh, it's too far down. There it is. Isn't that what we got? 6960. Again, do you see why you want a diagram? Why this is so cool to have a diagram? Because the diagram allows you to see all the moments, every possible place there's moment. And of course, that top one is the one we're after, because that's the max. Where do you notice that is? Where on the beam is that? It's exactly in the middle. So the place where we needed no beam for shear, we need way more beam for moment. So it's actually the maximum shear and the maximum moment that we got to look up in that table I showed you. Otherwise, the beam's going to break. You can't just pick the moment at any location you want. Let's take a picture of that. Let's get that over into our notes. I thought I brought this in, but it didn't show up. Why not? Yeah, there it is. This is, my friends, our moment diagram. Again, this is the simplest possible shear and moment diagram there is, because I just gave you the easiest possible force. I didn't add any individual forces, like there's a big point load. I let it go all the way across. It wasn't triangular. We have other kinds of loads. And so these diagrams are going to get pretty weird over time. But does it make sense? As I pointed out, we're interested in that, which should be the M max. That's why we drew this, because we want to find what's the maximum and where is it, so we can kind of choose the right beam. All right, how's your brain?
I mean, the moment makes sense.
Yeah. Can you see the place where breaking the beam is being a fixed connection? Therefore, it would make total sense to come in and say, well, that connection provides vertical support, V, shear, horizontal support, normal, which we don't need in this case, and moment support. It's connected, fixed connection. It's going to provide all of those. Good thing. Otherwise, that little section that we're looking at would be moving, and we need all the sections not to move. Every single part of this beam can't move. That's exactly the basis on which we did the truss problems, right? We ignored everything and just looked at one joint and said, this joint can't move. That's what we're doing here. That section can't move. And the answer is, it won't move as long as you choose a beam that can do 40, 60 in shear and 14,200 in moment. If you choose one that's allowable that can do those two things, then it will actually be capable of staying still. Just like in our truss, if we said, hey, if this member right here can handle 4,000 pounds of tension, then we'll be okay. Isn't that what we assign numbers to those? It's not that we just said, hey, there'll be 4,000 on this. It's you've got to go choose a piece of wood that can handle 4,000, and then we'll be okay. But if you choose a beam, if you choose something in that truss that can't handle 4,000, then whoosh, breaks and down it goes. Super cool stuff.
So did we not look at the horizontal force because it was kind of the same plane of the beam?
Well, there just
Going
wasn't
forward.
any forces on it horizontally. Does that make
Oh
sense?
yeah, so there wouldn't be any.
So we could do that, but we just say, there's none. In other words, the beam isn't going to have any forces pulling or pushing on it. Well, unless we come back and if we put an arrow pushing on it, at an angle someplace, then we'd have one. But again, loads tend to be because of gravity. So you tend not to have too many horizontal loads unless you add one yourself. So that's a great question. Okay, let's see if we can take this from the top. Before we go today. So here's a nice, lovely drawing. Let's try to do this one more time, but a little bit faster now. So I drew the walls that beam is sitting on. I told you it's 22 feet. I told you it has 312 pounds per foot of distributed load. And let's see if we can do this kind of quickly now. I'm going to do it with you. But let's chop it, say right here. And let's call that distance X where we chopped it. And let's have a blue shear. So to the right side of this, actually, I think I should probably redraw this. Red. So we're going to go out here. We're going to chop this beam right there. We need to figure out what the reaction there at point A is. We got to calculate that. And we've got all of these uniformly distributed forces up here that are 312 pounds per foot. And we know that because that's a fixed support, there's a shear. And right now I'm telling you, draw the arrow down, but we'll go into this a little more tomorrow or next time I see you, Tuesday. And we've got moment. I'm going to change colors so that I can make my notes look good. And we've got moment, and let's just leave it at that. There's those two forces. So please blurt this out. Let's kind of do this together, but I want to try to give you a chance to do this a little bit ahead of me. What's the reaction at A? You got to find that before we start. What's the reaction at A?
I got 3,432 pounds.
I got the same thing.
Okay.
3,432 pounds. So the first thing I've got to do is get the reaction at A. You would have went 312. Proceed on if you're okay with that. I would have taken 312 times 22, and that would have been all the load. And because this is symmetrical, I would have just cut it in half. So now your free body diagram. Do you see that is so important that we drew the free body diagram? That little chunk of beam is just floating in space right now. It just has arrows pointing at it. So shear. That's our second calculation. Which is nothing more than the sum of the forces in Y needing to be equal to 0, equilibrium. This is everything we've studied in this class all rolled into one now. We're actually doing some real stuff. So add up all your free body diagram, includes your fixed connections. So add them all up, set them equal to 0, solve for V. Leaving X as X, because X could be anything. So we're finding all shears. So don't you have 34, 32 pushing up? You have 312 pounds per foot times X feet pushing down, and you have V pushing down, all of which need to be equal to 0. You're done. V equals 34, 32 minus 312x. Bam. Shear equation. You know this is a line. As far as graphing this, like I'm probably on a test, all I'm gonna give you is what I just showed on my sheet right there, which is just a little place for you to graph this. Just find a couple of points that work. You know this is a line. So this is the V-axis, this is the X-axis. My beam is 22 feet long. At X is 0, I would have a shear of 34, 32. At X is 11, I would have a shear of 0. Like, just find points that work. At X is 22, I would have a shear of negative 34, 32. So shear is in pounds, X is in feet. And I have kind of the key answers to this now. I have at 11 feet, there's no shear. At 22 feet, there's negative 34, 32 pounds of shear. There's my shear diagram. Again, the only reason I really drew this is just to get Vmax. I'm not going to ask you that. All they'll ask in your assignment is to find the shear diagram, but that's the reason we did this. That's the reason we drew the shear diagram, which is just a picture of the shear equation. But the cool thing is, I know the shear any place I want to know now. Somebody says, hey, 2 feet in, what's the shear in the beam right there? That's where it failed. And, you know, we could actually go into that now. We have an equation. We have a graph that'll tell us. That's pretty powerful. That's pretty cool. Finally, moment. Some of the forces in Y are now 0, as long as we choose the right beam. Now we need the sum of the desire to rotate, the moments. We need the sum of the moments to be 0, sum of the moments. In our case, around A, because that's the side of the beam we happen to choose. We could be doing this on the right side of the beam. As I said, we'll talk about that Tuesday, but I need the sum of the moments to be 0. So what are those moments? Well, I've got M, which is the way I drew it, counterclockwise, so that's positive. And then I've got V going down a distance of X in. And then, and remember, these are weights, like that 312X was the weight, right? That 312X, I've also got 312X, which is all the red forces. So those are concentrated right here in the middle. That'd be 312X right there. And it's a distance of X over 2, just like it was before. So this is a force times the distance. 312 times X is a force. X over 2 is the distance. And all of that's got to add up to 0. If I just take this value for V right here and throw it in there for V so that I don't have too many letters, then I'll have this. Since I'm out of room, I'm going to finish it. So M is already positive. I'm going to add the other stuff to the other side. So if I add Vx to the other side, if I take that blue equation and multiply it by X, don't I get 3432X minus 312X squared? And then minus this equation, which is 312X squared divided by 2. I guess that'd be 156. And I'd be adding it to the other side, so it's minus, so I'd be adding it to the other side. So that'd be plus 156X squared. And then I just have a couple of squareds to add together. So M equals 3432X minus 156X squared. That is my moment equation. Moment. Again, meaning I now have every moment. What I'm interested in is the moment max, but let's make a graph of it. Again, I'll have 22 over there. And at X is 0, notice 0, 0 is an answer. And it turns out if you put 22 in, it's also 0. So 0, 0 is an answer to this, and so is 22, 0. This is still X in feet, but this up here is moment, which would be in foot-pounds. So now I just need to find some other points. Some other points that work to make the graph. If you can tell this is an upside down parabola, then you might be able to tell that its peak, maybe you remember your, your calculus 1. You can find the maximum by taking this derivative and setting it equal to 0. M prime is equal to 0. M prime would be 3432 minus 312. 312x equals 0. 3432 divided by 312 is, hey, it's in the middle. X equals 11. It's in the middle. So now that I know that, I can stick 11 in. So what is M of 11? I can put 11 in. 3432 times 11 minus 156 times 11 squared. Woo, 18,876. Again, you could just get a graphing utility out, use Desmos, whatever. You can graph this any way you want to. But notice I don't really need to do that stuff. I can kind of graph that point. I can now label it as 18,872, and then I can just kind of sketch the parabola since I know it's a squared equation. Parabola is going to look something like this, and so cool. Moment diagram is complete. Moment diagram. So moment max, V max, I found both of those things. Let me show you something really powerful. I'll leave you to think about this. What did you notice when I took the derivative of that? I took this equation up here to find the maximum, which is where the slope is equal to 0. I took the derivative and I got 3432 minus 312x. Where have we seen that before? Isn't that the shear equation? That's not a coincidence. The moment max happens when the shear is equal to 0. In other words, I could have actually known that. We'll talk more about this next week, but there is some deep magic here that is glorious in terms of math and calculus and so forth. So the fact that the shear was 0 actually coincides with the moment being maximum. The place of no shear is the place of maximum moment. That turns out to always be the case. Rather fascinating. So again, what's so cool about the moment diagram is I have the moment any place I want to know now. So armed with the V max and with M max, I could now go to that chart, choose a beam, and I would actually know that internally it's not going to pull apart. That's pretty darn powerful. Boogie if you need to, but I just want to show you one other thing super quick here. If I can find it fast. I showed you this page that I have to turn into the city when I draw a house plan. But do you notice what's sitting right here on it? Do you see how it lists positive moment? And it says 31,577 pounds, and that's 94% of what's allowable. Why is that what's allowable? Well, notice the beam I chose is 3.5 by 14. I showed you in the chart a second ago how you can look up what allowable moment that is. And what this is saying right here is this is how much moment is going to be needed. See, that's the number you just calculated a minute ago, 18,872. This is a different beam. But that's how much is required. That's what's going to be required in this at the maximum location, which is in the center of the beam. And that's 94%. So maybe in the chart, the 30.5 by 14 was, say, 33,100 or something. So in other words, you got to choose a beam that's stronger than what's going to be required. Notice how much shear is going to be produced in this particular beam, 6,500. Notice the beam that I chose, that's only 61%. So the shear value of that beam must be huge. It must be like 9,000 or something like that. Must be way stronger. I mean, you see that these are the main calculations I have to make to actually design a beam for someone's house. Like you're doing it now. You're engineering now for the first time. You're actually doing what I do. Now, you know, what am I actually doing? I'm punching all this stuff into a machine and getting the answer popped out. The first time I ever calculated this for a house, I turned in the calculations like you and I were just making. And because they don't know engineering, they said, I don't even know what to do with this. Do you have one of those pieces of paper that, you know, has a bunch of percentages on it that all say something less than 100%? That's what they wanted. They wanted the machine calculation. And I get it, because the machine's not going to make a mistake. And then they don't have to know engineering to check my work. But it's like, we're doing it now. Like, you're there. Real beams have distributed loads. Look at all those arrows. You understand that now. You now understand what the positive moment, what the maximum moment is, and how to calculate it. You know how to calculate that now. Shear, you know, to calculate shear. It's pretty cool, isn't it? So what we'll do next time is we'll try a triangular load. What if the load's not so simple? What if it's triangle? What if it's trapezoid? We'll start playing around with different kinds of loads, and we're going to get some really fun graphs. And so it's very exciting. So I apologize. We have to wait till Tuesday because I want to start it right now, but we can't. All right, get out of here or stay after if you have time and have questions for me.
All right. Thanks, Doug.
Yeah, have a good day and weekend.
Yeah.
All right, thank you.